as an introduction to those of you who are not familiar, this is a colleague of mine, Chami Amarasinghe from LZ. He will be talking about anomaly finding within our dark matter detector. So Chami, if you want to share your screen and take it away.
Okay, thanks. All right, thank you, Austin and Richard. Okay, so hello, everyone. My name is Chami. I'm a graduate student at Michigan. I started my third year. I'm going to talk to you about anomaly finding in the LZ dark matter experiment. This is some work that I've done in the past couple of months with two other collaborators in LZ, Scott Kravitz and Maurice Authors. Okay, so first a brief, I guess, introduction to what the LZ dark matter experiment is for those of you who are not familiar with it. LUX-ZEPLIN, so two names of its predecessors. LZ is an upcoming underground direct detection experiment in Leeds, South Dakota. And just a simple introduction here. On the right diagram, you see it's the inner heart of this Russian doll that has many layers. And it's this time projection chamber, or TPC as we call it, that's filled with liquid xenon. And the basic operating principle is you have a incoming particle, be it a electron or a photon or a WIMP or a neutron or whatever, and it comes and interacts with the liquid xenon, which immediately produces scintillation light. So this is a property of xenon that makes it very attractive to the dark matter and neutrino community. So it initially produces the scintillation light when an interaction happens, which is then detected by these arrays of photomultiplier tubes on the top and the bottom. In addition to the scintillation light, it also produces several ionization electrons. So the xenon is ionized. And these electrons are drifted up to the detector by an electric field, where they are extracted into a gaseous xenon layer, which in turn scintillates and produces a secondary signal called the ionization signal. So these signals, the scintillation and ionization, are called S1 and S2, just for brevity. So this is an example of a waveform that one might observe. So on the x-axis is time, and you have the several photons detected by the photomultiplier tubes, and this is the primary S1 signal. And after a certain amount of time, you have the S2 signal, and this time is reflective of the distance that these electrons traveled when they're drifting up into the to the gaseous region. So this is what a typical event could look like. It could have several other pulses that are sometimes spurious, sometimes not. Sometimes they have to do with the size of the S2. And in general, it's usually a pretty complicated waveform that we deal with most of the time. So anomaly finding in LZ, briefly stated, our goal was to quickly identify and interpret anomalous data in high dimensional spaces. So before we talk about high dimensional spaces, let's first quickly talk about the simple low dimensional space that if you're doing an analysis, you'll likely be working with. So this is what's shown in this plot here. On the x-axis, we have the size of the S1 in the units of numbers of photons detected. And on the y-axis, you have the size of the S2 in a log scale, because usually the S2 size is much bigger than the S1 size. And this is all simulated data. And you can see two distinct populations, one corresponding to electronic recoils, which is when whatever interaction happens in the liquid xenon has to do with the electrons directly, as opposed to interacting directly with the nucleus, in which case you get a nuclear recoil. And you can see that these two distinct types of recoils or interactions are separable in this S1 and S2 space. And this is another good reason why liquid xenon, xenon in particular, is so attractive to dark matter, to the dark matter community, especially because of this discrimination that's possible. Because we're searching for primarily WIMPs, which interact with the nuclei of these atoms. So we want to separate our WIMP signal away from the large electronic recall background that we have. Specifically, these two populations correspond to, in the electronic recall case, a benchmark for an ER source, which is tritium, which decays with a beta particle of, I think, 18 keV or so. And the nuclear recall population here is typical of a 40 GeV WIMP, assuming standard astrophysics. Okay, so this is our basic analysis space. But in addition to S1 size and S2 size, we have a whole lot of other features that we can use. And the jargon for this is reduced quantities, or RQs, using RQs and features interchangeably. So like I said, in addition to pulse size, you can also talk about pulse shape. And there's good reason to believe that pulse shape encodes useful information about things like the nature of the interaction and sometimes even where in the detector the interaction happened. This is especially the case for liquid argon, where pulse shape discrimination is really useful for doing this, this kind of discrimination between ERs and NRs. So a summary variable of how one might encode pulse shape, for example, is what is the amount of time that it takes for the pulse to reach X% of its total area. And if you calculate that for several X's, you have a good summary of what the shape of a pulse looks like. And this, of course, means that you don't have to directly work with waveform information, which is useful in terms of speed. Oops, sorry. Okay, so pulse shape and size. You can also talk about 3D position, where exactly in the detector the interaction happened. You can talk about signal distributions in space. So what I mean by this is, if I go back to the previous image where I have the arrays of PMTs, each of these PMT channels can record exactly how much light they individually saw. So we can look at the spatial distribution of how much light they saw, and you can come up with, you can derive quantities from those that are summaries of variables like how concentrated is a certain event or how diffuse is a certain event look like. You can talk about numbers of pulses in an event, and one might assume that an event that has a lot of pulses, there's an argument that it's more complicated than all other pulses, so we should look at it closer and see where all of these pulses are coming from. So these are just a few examples of the features that you can use and that you can put into your algorithm. And what can you do with all this? Well, it depends. You can identify rare backgrounds. If you know what you're looking for, if you know the type of background that you're trying to discriminate against, you can select your RQs in such a way that you have the best discriminatory power to remove these backgrounds. These RQs can be used in algorithms to help tune programs and like software that we have in our data processing pipeline to select certain events or select certain pulses. And so there are efficiencies associated with these software, and a general purpose anomaly finder can help to tune these software to maximize our efficiency. We can also use techniques like this, using these RQs to help us with performing manual data quality checks. It can help speed up these processes. And of course, eventually, when we have real data, we can use these to pick out anomalies in real time as the data is coming in. Okay, so those were some of the RQs that we want to work with. And so we take advantage of these high-dimensional spaces and explore two unsupervised learning techniques for finding patterns and anomalies in the LZ simulation data. And I'll be describing these two briefly in the next couple of slides. The first one is the isolation forest, and the second one is a combination of TSNNE dimensional reduction with some clustering going on. Okay. So firstly, the isolation forest. Essentially, it's a collection of random trees. And the way you build such a tree in this forest is, so you mirror the root node. You pick a random feature and you apply a uniformly random cut on this feature. And so this naturally separates your data into two sets, one with the values of the feature being less than the specified cut and one with values above. And at each of these nodes, you do the same thing recursively, pick a random feature, apply a uniformly random cut until you have separate data points. And the way that outliers are detected in this setup is that assuming that the outliers are few and far away from general populations, outliers will take fewer cuts to isolate. And we can see an example of this here in 2 dimensions. So you have a distribution of data in X and Y, whatever those may be. The outlier here, far away from the general population, takes only 4 cuts to isolate, whereas a point somewhere near the centroid of this distribution will take many more cuts. So that's the basic principle. You can use the number of cuts made to isolate a point as a proxy for anomaly score. And there's a more specific definition that you can make, which is a function of the length of the decision path. And so one such definition is plotted here. And this is the anomaly score distribution. Of course, you can see that there is a large number of events with a very low anomaly score. And these are, of course, these belong to these general populations. And there's some outliers that are presumably far and away from the general distributions. You can set the anomaly score threshold to be whatever you want it to be. So if you want to keep very few anomalies, you can set it at a high value and so on. The advantage of the isolation forest is it is directly interpretable. So you can ask questions like why a certain event is anomalous or why a certain set of events are anomalous. The way you do that is you consider the branches where the decision paths are short. So by construction, these are the branches where the anomalies are because they take fewer cuts to isolate. Now, if you take a collection of these branches and you loop over them and you count which feature is cut, and you basically histogram these counts, you'll end up with a plot like this. Now, the more features are cut in these short decision paths, the more features that are cut on are the features that contribute to the anomaly, to the abnormality of these points. So we have a direct way of seeing which features are responsible for a point to be considered anomalous in this very high dimensional data space. So like I said, this is an example. And you can see that the feature that's considered most important in this case is the size of the pulse after the S2. And the second most important is the S2 pulse area at 200 nanoseconds, for example. And you can plot these two variables. And here is our anomalous data point that corresponds to this point. Likewise, so this is just for one data point. You can ask the same question for a set of data points and get similar answers. So this is the main benefit of using a technique like the isolation forest. It's that it's interpretable, which is important when you're trying to discard data or something. You have to have very strong justifications of why you're doing that. Okay. So switching gears to TSNNE clusters. TSNNE is a more involved, like sophisticated algorithm for dimensional reduction. So the main goal here is to go from our very large 30-dimensional feature space and compress it down to fewer dimensions that we can visualize and work with. So 2, 1, 2, or 3 are all good numbers to visualize the data space. So we use another clustering algorithm called dbScan to pick out the different clusters after the compression has been done. And ideally, we want to find out why these are being clustered as they are. So this plot on the left here shows an example of that, where we go from our full data set of 30 features in all their glory to 2 TSNNE variables. So all these features have been compressed into 2, TSNNE1 and TSNNE2. And you can see that they form pretty distinct clusters, this big yellow blob in the middle, and it has some satellites orbiting it. Just looking at this plot isn't very, it doesn't tell us a lot. So we have to, as a first step in trying to understand it, we can map it to a space that we're familiar with. And that is the S1 versus S2 plot that we saw before. So what we do, we keep the colors and map it into S1 versus S2. And we see something interesting in that some of these TSNNE clusters map directly to populations that we understand in our simulation data. For instance, this the red population and the purple population, we have an idea of what they are. The yellow population is the electronic recoil band. One thing we don't understand, at least if you were to look at this plot without the colors, is why are these cyan data points interspersed in the ER band? So that's something that we wouldn't be able to pick out if we just looked at an S2 versus S1 plot. And this brings us to some of the applications of anomaly finding and clustering and dimensional reduction. Firstly, just to explain what the cyan population is like, what that is. We have a program in our data processing pipeline called the pulse finder, where it looks at a waveform. A waveform has several pulses, and it looks at each pulse and gives it a label, like S1. This pulse is an S1, this pulse is an S2, and so on. And it does so by defining some boundaries in time as to where the pulse starts and ends. So we found that the cyan population in TSNNE space here that's interspersed in the ER band all have events that take a long time for the pulse to start after the pulse boundary, after where the pulse boundary had been defined. So this is a problem in how this pulse finder was operating. This was also confirmed by putting it through the isolation forest and seeing what feature it was that caused this cyan population to be anomalous. So the isolation forest feature interpretation told us that these events have a long rise time. So this bug fix was implemented in the pulse finder, and here it is after, which is a properly defined pulse boundary. So that's one example in which we did not know what we were looking for, but we threw the kitchen sink at it, and it gave us something that we could improve on in our simulations and data processing. A second example has to do with a rare background called the gamma X background. And we don't really need to know exactly what this is, but briefly, it's what happens when you have a photon that's multiple scattering inside your detector. And one of the scattering sites happens in a location where there's improper charge collection. So the ionization signal isn't properly collected. And so in these types of events, we have artificially lowered S2. And this could interfere with our signal regions. So what we did here was we picked some RQs that we know that we had a good idea that were going to be pretty strong discriminators against this gamma X background, and we put these variables in the isolation forest and let it build its trees and identify anomalies. And it identified these gamma X backgrounds at a very high success rate compared to the single scatters. And so this table was generated by comparing the outlier points of the isolation forest with the simulation truth data. And so, yeah, we have a 95% success rate of identifying these gamma X with a pretty low leakage. So this is an example where we know, we know what we're trying to look for, and we devise craft some variables that still can be high dimensions. So I think in this case, there were like 10 features that were used in this. So something that's kind of difficult to do with a simple cutting analysis, you can just put into an unsupervised anomaly finder, and it'll pick these out for you if you choose the right variables. Okay, just as an aside, the reason I presented two techniques is we want these two to be complementary. So this is just like just a nice picture, nothing more, about showing that these two different techniques, the isolation forest and the TSNNE clusters, could be working together to identify the same sorts of populations. So what's shown here is a plot of the data in TSNNE space. So just the compressed variables TSNNE1 and TSNNE2, and in yellow shown are the outliers that the isolation forest considers. And as you go from one plot to the next, the bar for the isolation forest to consider a data point anomalous is lowered. So more and more anomalous data points are being considered. And you can see that what was the cyan population in TSNNE space is considered completely anomalous by the isolation forest. And as you lower this bar, these clusters seem to be eaten up from the outside. And we thought that was pretty cool. That maybe a metric for how anomalous a point is in TSNNE space is the distance from that point to the centroid of the cluster. Some heuristic like that, but we haven't confirmed this. And as of now, it's just a nice picture to see that these two things might be complementary and considering the same things, even though they're completely different techniques. Okay. So unsupervised techniques have a great power in probing the known unknowns, which is usually what we consider the domain of other supervised kind of techniques. But also the bigger advantage is that we can probe the unknown unknowns, in which you throw everything at the algorithm and hope it finds something that you're missing that you haven't considered. So that's one of the two main points that I wanted to convey. The second point is that interpretability is extremely important for studying events and groups of events, especially if you're trying to, based on the output of these algorithms, if you're trying to formulate a cut to discard some events or something. The justifications for a cut using machine learning understandably have to be extreme. So you have to have a very, very clear understanding of what you're cutting. And interpretability in the case of the isolation forest goes a long way in giving you that. Also demonstrated early successes of what we've done with these techniques. And these include data quality, the efficiencies of your data pipeline algorithms, like the pulse finder, for example, anomalous backgrounds, and it can help in, like I said, tuning other algorithms and fixing the possible bugs in them. Okay, that's my talk, and thank you very much for listening.
Excellent.
Thank you, Chami. That was great. I have a question, if you don't mind.
Yeah, of course.
Back on slide 6, when you introduced the TSNNE algorithm,
yeah,
you have here maybe 1, 2, 3, 4 distinct populations, and those 4 different colors. Yeah. Are you predefining the number of clusters that this algorithm should find, either the TSNNE or the DB scan?
Yeah, so the answer is no for TSNNE. So TSNNE does not have any a perception of clusters. It just puts them in this space, and we're using a different algorithm to identify the different clusters. So and you can see some black points here, and those have nothing to do with what the TSNNE algorithm is doing. It's just the the points that the DB scan clustering algorithm considers not belonging in any one cluster. Yeah.
Okay. Is there anything, have you found anything interesting about those particular points, those black points?
No, we haven't. And I think this is just the existence of these black points. I think we've checked all of these, and well, these ones are supposed to belong to the yellow, but DBScan is not doing a very good job at identifying that. Yeah.
Okay. Great, thank you.
Yep.
If anyone else has any questions, feel free to go ahead. Otherwise,
could I ask one?
Yeah, please go
I
ahead.
know I'm not supposed to, but I don't want to shut out any students. So, but just so with respect to Gamma X, or just in general, obviously there are. So in the case of Gamma X, one specifically knows they're going to have this elevated S1 relative to S2.
Yeah.
So just so I can understand, in that case, were you just using features? So how do you avoid basically the actual information that the S1 S2 ratio is off from contaminating the decision about identifying it? I'm afraid I was, as you were going through, I started asking myself that question, then realized I couldn't answer it. It may be obvious. You may say, no, Rick, don't worry. The parameters that we had definitely would not pick up on the fact that the S1 S2 ratio is simply off.
Yeah.
But how did you make? Because that's always one of the challenges associated with trying to develop new discriminants, is just to make damn sure they're not simply using something you already know about, which is effectively.
Exactly. Yeah.
Yeah.
So firstly, before we put the data in any of these algorithms, we made sure to decorrelate everything. And if that wasn't enough, at least for the Gamma X classification, we explicitly
Chami,
did not.
I'm so sorry. You're going to even have to explain to me what decorrelating in that sense means.
Okay. So in the case of variables like S1 and S2 sizes and pulse shapes, obviously these are all super correlated to each other. Like if you, if the first half of your pulse is big, then the second half of your pulse is also going to be big. So we made sure to give the algorithm only the most basic summaries of whatever class of variables we're talking about. And in the case of Gamma X, we did not give it S1 size, S2 size. We did not give it any pulse shapes. The only important variables we gave it were things like the size of the interaction cluster as observed by the PMTs. And these, of course, were not correlated with S1 size and S2 size, which we made sure to verify. So we gave the variables that are important to the Gamma X were things like how concentrated were the size of the clusters, and what is the fraction of the light that the for example, in the bottom PMT array, one of these PMTs saw the most fraction of the light, and what is that fraction over the entire sum of the bottom PMT. So these were the variables that the algorithm found extremely important in discriminating the Gamma X's. And we made sure that the variables that we gave it were not correlated to S1 and S2. Does that answer your question, Rick?
Yeah, no, I mean, so is there, so in the past, and you've probably seen this with machine learning, it's very good at picking up things you missed that somehow conveyed information. What's the point? You're asking it to do a discrimination on the pure data, but it turns out that somehow a clue is sneaking through in the data, which is not, it's not a real, is not a part of the real description, but just somehow got accidentally encoded. Now, I will grant you that given you're only using what, 5 or 6, I'm sorry, I've forgotten now for this example, 5 or 6 numbers that are being fed in, and as you say, they're pretty well understood statistically, and therefore it's difficult to. I mean, one of the ways that sometimes things sneak in is just you have a statistical measure of spread in S1 versus S2 or something like that, for S1 signal and what have you. But what one doesn't realize is, oh damn, it also has just a simple height dependence. So you're effectively indirectly giving it information about the size of the S1 event. And when you combine that with the fact that the events you chose to pick all had very similar S2s, it means that the absolute value of the S1 height was a good indication of whether this thing was a gamma X or not. And
Got it.
And I was just wondering how you typically protect yourself from those kind of
Right.
unintended encodings when you're giving it. Do you see what I mean? I mean,
I think so.
Yeah.
Can I explain to you what I think you mean? So in whatever distribution of variable you have characteristics of that distribution. Like for instance, an S1 distribution, you have its height, its width, and so on. And even if you do not give the algorithm specific information regarding the S1, it may pick up correlations of the mean and of the width of this S1 distribution in other variables. And then it can somehow infer information about the S1 distribution. If that's what you're asking, then one way to remove that dependence is all of the data that's been fed into these algorithms has been the mean has been changed to 0, and the variance of that distribution has been constrained to unity. And so I don't think there's anything more you can do to remove other correlations other than explicitly changing the shape of the distribution. So yeah, just by normalizing both the mean and the variance, you can get rid of these other correlations that might sneak in.
Got it. Just a very simple follow-up, and it would be good for the others to ask some questions, but is there a way in which this differs from sort of more traditional principal component analysis? If you were to describe how it differentiates itself, is it just in the nonlinearity?
So
go ahead. Yeah.
The TSNNE in particular is kind of like a nonlinear PCA, but the basic technique is different. Like it defines a probability distribution in this very high dimensional feature space. And then it defines a similar distribution in the low dimensional feature space that we want to go to. And then it compares these two probability distributions and minimizes some metric that retains the most information in this high dimensional feature space to the low dimensional feature space. And it does that in a nonlinear way, while PCA does the same thing, but using linear combinations of these features. So in that sense, it's more powerful and can pick up connections between the data that PCA would probably not be able to do.
Have you tested this similar method using PCA instead of the TSNNE?
No, we have not. We went straight to TSNNE, but that's something that we should do. Yeah.
Cool. Okay. Does anyone else have any other questions? Oh, Jan, looks like your hand's up.
Can I ask one? Just on these slides, I know this because I work in LZ. If you look at the plot on the right, so the yellow can be categorized into many other small clusters. There's one cluster above the ER band. There's other like scatters near the right. There's also like the scatters between the ER band and NR band. So what are the parameters like you can tune to like get all those classified?
I think so. Yeah, one aspect of that question is how well we're doing the clustering and coloring of this TSNNE plot. So you can see, like, I mean, there are like some divides even in this this one yellow blob that a case could be made that these are separate clusters, and our clustering algorithm didn't do a great job at discriminating them. So if we do that and map it back into S2, S1 space, we could see these other clusters being differentiated also. I don't have, we have done this analysis before, and you can, I don't have a plot to show you right now, but you can see that this like outgrowth from the ER band and some of these events that clustered that could be part of the NR band are identified as, within, as being subclusters of this larger blob. So yeah, we have, unfortunately, one limitation in how exactly we're doing the clustering in interpreting the results of TSNNE. Did that answer your question, or did I miss it?
Yeah, sort of.
Okay.
Yeah, and looks like your hand is up if you have a question.
Yeah, it's a really simple question about isolation trees or isolation forests. It strikes me that you have to have some criteria that depends on the extensivity of the data. So in other words, if you multiply the data by 10 times, then all your isolated clusters will have 10 times as many objects. And forgive me if this is obvious, but is it just scaling by percentage of data? That is, if you normalize by the numbers, you get the same number of cuts? Or is your cut on what is an isolated and what is not an isolated, does it depend on linearly on how many things you have in your sample? That is, how many rare things actually happen right next to each other because you have so many events?
So could you, could you clarify what do you mean by multiplying your data by 10? Like, do you mean if you had like 10 times more data points?
Yeah.
Okay.
Yes. So the idea is things which are easy to isolate are easy to isolate because they're isolated. But of course, when you have many more data points, they're no longer isolated.
Right. Yeah. But if you populate, I think if you populate your 10 times more data points in according to the same underlying truth distribution that your initial data was in the first place, then I don't think it'll affect the anomaly score, because in a sense, those isolated data points will be as isolated even with 10 times more data, because there will be so much more data points in the central distribution.
Well, you'd actually hope that their isolation would improve, as it were.
Exactly. Yeah.
Just because Poisson fluctuations are becoming less, less important.
Right. And yeah, this technique is pretty robust, assuming you have a good number of trees, and the results are pretty consistent, and it kind of insensitive to the number of features you have, and maybe, I haven't checked this, but maybe to the number of data points you have.
So the idea is that the number of trees would, all the statistics for every object would go up linearly with the number of data points, and so the relative separations would stay the same.
Yes. Yeah.
So in that sense, when we talk about isolation, it's not the visible white space. It's more that does it effectively model sort of Gaussian-like PDFs around these, but multidimensional PDFs around the point clusters, and just looks for the hypothesis that effectively allows you to characterize. Actually, I've realized, yes, okay, there's another thing I don't understand about isolation forest. Is there a prior in the sort of the generic shape in this multi-parameter space that these different clusters are supposed to, have, or is it the space between them that, if you like, has your generic model and you're seeing how many of those white spaces you can insert with some, general shape sorry, I should understand this at a more fundamental level, but I don't, which is why I'm asking the question.
So I don't, there are no priors in this case, because each, I think maybe the crux of your question has to do with why a uniformly random cut is applied. So you could have any distribution of data points, and you take the max and min value, and in between those, you choose a uniformly random cut. So if a feature is isolated from the others, and if there are few of these isolated features, it is much more likely that they be separated very early on in your series of cuts. I think you could bias this technique in a way if you, instead of choosing a uniformly random, instead of choosing a value in a uniform range, you could choose a value from a weirdly distributed range, and that could maybe overemphasize the importance of the presence of outliers in that sense. But I don't know what's a good.
Okay, so you're saying, you're saying I'm basically thinking about it wrong. It's just a question in each. Yeah, I mean, sorry, I realized you were describing that, and I was just being closed-minded to it. It's more about simply putting in arbitrary boundaries that are capable of dividing off points or groups of points. Yeah. So the way I was thinking about it was wrong. It's more based on the binary, like a bit more like a BDT, as it were.
Right. Yeah, and you could generalize this to something more in which there is a variant of the isolation forest where instead of just cuts being applied in X and Y, you allow yourself to rotate in the parameter space. So in the 2D example, you could be able to apply skew cuts that have a non-zero slope or non-infinite slope, and in the high dimensional case, that's the equivalent of that is you're cutting in like these hyperplanes, and that has been shown to be faster than this standard vanilla technique of applying straight cuts in the isolation forest, which is interesting.
No, that was probably one of the clearest talks I've sat through recently. I mean, obviously it's material I know a little better in terms of the underlying stuff, but irrespective of that, it was extremely clear. Thank you very much.
Thanks for having me. It is.
Chami, we really appreciate you coming in.
Thank you, Austin.
I certainly appreciated it. So thank you so much, and we will be in touch.
Okay, sounds good.
Yeah.
Take care.
Have a good rest of your day.